Hi everyone, my name is Zohreh Davoudi and I will be giving two lectures on quantum simulations of lattice gauge theories. The first lecture is going to be on the topic of Hamiltonian formulation of lattice gauge theories. That is going to be the language of quantum simulation. And in the second lecture, we will be discussing various approaches to quantum simulation, particularly in the context of simulating gauge theories. So with that, let's get started. These are the topics that we will be covering in lecture number 1, which is going to be again on Hamiltonian formulation for lattice gauge theories. So we're going to learn what are the differences and similarities between the Hamiltonian formulation as opposed to the Lagrangian formulation that most of you should be familiar with. We're going to focus on a formulation by Koget and Susskind, although this is not the only formulation you can imagine for discretizing a lattice gauge theory, and then simulating it using a Hamiltonian formulation, but this is the most common and standard one. We will talk about basis states, Hilbert space, and constraints, as well as other formulations that you can imagine, as I said, along with several features that would make them advantages or disadvantages with regard to certain problems that you might be interested in. These are the topics that we will be discussing in length in this lecture. The second topic, which is how to perform a classical Hamiltonian simulation given the formulation in hand, I will just mention them in passing along with several references that you can check out because of the sake of time, although one of the exercises is going to be closely related to applying one of these classical simulation methods, which is the trivial one, the exact diagonalization. However, there are other methods, including a strong coupling expansion, exact and approximated diagonalization methods, as well as more efficient and advanced tensor network methods. So with that, let me get us started. With the Hamiltonian versus Lagrangian formulation. I should mention that the notes that I will be providing for these lectures are far more detailed and extensive than the set of recorded lectures and the associated notes are going to be. So I strongly encourage everyone to go through the longer notes that I will share with you after these lectures so that you have more examples and explanations for some of the topics that I will be introducing. So why do we like to do Hamiltonian formulation? Well, as I said, it's a natural language for quantum simulation. Traditionally, we are used to think about Lagrangian and path integral formulation to perform non-perturbative lattice gauge theory simulations, and it is important to understand how they compare. And with that regard, I'm going to build a table here. Let's try to understand and differentiate various different basic properties of the two formulations when it comes to simulating lattice gauge theories. So let me have a column that is called Lagrangian or path integral formulation. And let me also have a column that I call Hamiltonian simulation in short. All right. So what are some of the properties? Well, first of all, we have to identify the degrees of freedom in each of these formulations, degrees of freedom. And of course, in the Lagrangian language, we talk about fields and the derivatives of the fields. Fields and their derivatives. For example, if you're talking about a scalar field theory of one flavor, it's going to be either phi and then some derivative of the field phi as well with respect to space and time. Okay. On the other hand, in the Hamiltonian simulation language, we still talk about fields, but also the conjugate variables to the fields, right? So fields in their conjugate variables. And again, in the example of a scalar field theory, this would be phi, and then some pi, which is the conjugate variable to phi. So, for example, in the simplest case of a harmonic oscillator, a 0 plus 1 dimensional theory, we can imagine the usual momentum and the position operators to be representing the fields that we care about on the Hamiltonian simulation. Now we're just generalizing this to the field of space, okay? So another important difference is a space-time signature. Of course, no one forbids you in doing a real-time Minkowski calculations using the path integral formulation. Although in the end of the day, from the perspective of computational cost of the calculation, it doesn't make sense to do it that way because we would like to do important sampling through Monte Carlo methods. And that's why we often choose Euclidean time signature, which means that the time is imaginary. Well, what about the Hamiltonian simulation side? Again, no one forbids you to do a Hamiltonian formulation with imaginary time. That would be imaginary time evolution that could be useful in certain problems. But again, often it is more natural to just do the Minkowski real-time signature. And this is one of the reasons that Hamiltonian simulation is appealing to us, because it can take us from the realm of possibilities in the path integral simulation with Euclidean Monte Carlo-based methods to a new set of observables that are dynamical, as I will talk about. So the starting point, so let me have the separation of columns. Okay. So the starting point for a path integral formulation is, of course, the Lagrangian, which is written in terms of the fields and their derivatives. For example, in a scalar field theory, the Lagrangian would be a function of phi and derivatives of phi. On the Hamiltonian side, of course, this is going to be, the starting point is Hamiltonian. And Hamiltonian is again a function of phi and the conjugate variable to phi. In this case, I'm going to call it pi. Okay. Depending on what field theory you're dealing with, these could be different variables, of course, as we will see with the gauge theories later on. Well, what about Hilbert space? Well, it turned out that we don't actually deal with Hilbert space directly in this path integral formulation, so not dealt with directly. One of the reasons being we are in Euclidean space-time signature, and what we're interested in terms of the physical Hilbert space are Minkowski real-time states. So we have ways to get at these properties of these states, but we usually don't think about Hilbert space that explicitly in the path integral formulation. On the other hand, in the Hamiltonian language, it's very natural to think about the Hilbert space, and it's very necessary in the way that it's being built out of actions of the Hamiltonian or powers of Hamiltonian on some sort of vacuum state where all the excitations of the fields are empty, and then you start exciting them with the actions of the operators in the Hamiltonian. So what about expectation values now that we have the Hilbert space defined? Well, expectation values on the path integral language, as we all know, are coming from the path integral over all the possibilities for the fields. For example, in this scalar field theory, the possibilities on the field phi, e to the minus s, which is a function of phi, and again, derivatives of phi, times the operator itself. And that's really the integral that we take, we discretize, we importance sample, and calculate observables, for example, in lattice QCD from. On the Hamiltonian side, it's, again, pretty natural. In fact, that's the quantum mechanical definition of an expectation value, which is just the matrix elements of the sum operators in terms of the fields or the conjugate of the fields that is acting between the states. The states could be whatever state in the Hilbert space or eigenfunctions and so on. Okay. So can we have access to dynamical quantities? Well, the answer is yes and no in the path integral formulation. In fact, we know that in certain systems and problems, we can apply some indirect mappings to get access to dynamical scattering amplitudes from the path integral formulation or lattice QCD method, but not in general. So only indirectly accessible and of course we know, so in just certain problems, and you have already learned from very nice lectures in this summer school that the way to do this is through Lucher's formalism and various generalizations. But in general, if you're interested in real-time dynamics of a non-trivial state, that's not accessible at the moment because we're limited to Euclidean expectation values. Well, on the Hamiltonian side, this is always in principle possible. Of course, in principle. And this is because, again, dynamical expectation values are nothing but expectation values of operator psi between time-dependent state in this case, which is in this language just the psi at 0, e to the iht, o e to the minus iht times psi at 0. Okay, so as long as we know how to evaluate this with the Hamiltonian framework, then we have access to any kind of dynamical quantities as well. Okay, so what about the computational challenge? So from lattice QCD program, which is based on path integral formulation, we know that there are very efficient algorithms that would allow us to access certain quantities easily. Okay, so it's efficiently applicable, unless, of course, you're in situations where you have to deal with signal to noise problems or the sign problems. For example, unless for finite density and finite chemical potential calculations, or for, again, real-time quantities. Right? So then you run into signal to noise, degradation problem, as well as the sign problem. Okay. What about the Hamiltonian formulation? Well, again, the computational cost of these calculations is pretty high. And in fact, one of the reasons that we didn't really push for a long time the prospect of these Hamiltonian simulation using classical resources for lattice gauge theories is exactly this, because there is an exponentially increasing problem in the size of the Hilbert space. So Hilbert space increases exponentially with increasing the size of the system, and therefore classical computations are pretty hard. So the way to progress is to use maybe more efficient ways of going about this using tensor network ansatz. Although these kind of calculations have not yet been advanced to the point that we can do higher dimensional QCD calculations with such methods, but at least that's one way forward that people are excited about. Another possibility, and why we're kind of excited in the prospect of this program once again, is that we could do probably quantum simulation or computation here, so that we can deal with this exponential increase in the size of the Hilbert space using quantum resources. And that's the promise. And well, we'll talk about this in more detail, of course, throughout these lectures. Okay. What are the computational methods that have been thrown at this problem? With the path integral formulation, again, as I said, we resort to Monte Carlo samplings plus all sort of advanced algorithms for computing correlation functions. Okay. On the Hamiltonian side, again, if we have to resort to classical resources, there are methods like exact diagonalization or their approximate form. Again, there could be tensor network approaches. And again, as well as quantum simulation. And this is the area that requires a lot of development. It is just the starting, and it takes a while before we have the same comprehensive and mature program that we have on the path integral side for lattice QCD on the Hamiltonian simulation side, particularly with quantum simulation technologies. So hopefully by the end of these lectures, you would recognize some of these interesting directions to pursue if you're interested. Okay, so just a note on this problem of exponential increase in the size of the Hilbert space. Let's try to make sense of it from the perspective of the Hamiltonian evolution, right? As I said, primarily one of the reasons that we want to do Hamiltonian simulations with a quantum computer is to get access to dynamical quantities, right? What that means is that we are going to have to deal with this time evolution operator from quantum mechanics that is acting on some state that we have prepared, that we're interested in its dynamics. And that's also a non-trivial step by itself, how to prepare this state. Act by E, which is this time evolution operator for simple time-independent Hamiltonian, could be something like this, times psi, okay? So unless this state psi is already an eigenstate of the Hamiltonian, this dynamic could be complicated. Why is that? Well, if this state is not an eigenstate, then what would happen is that e to the minus IHT is acting like many, many operations of the Hamiltonian on the state that would start to mix the state of interest into any other state in the Hilbert space that respects the same symmetries as the original state. So it belongs to the same symmetry sector as that state side. Otherwise, it wouldn't mix. So you can already see that even if you start from one state, you have to explore an exponentially large number of possibilities throughout your dynamics if you're not starting from an eigenstate, right? And therefore, that's a computationally demanding scenario. And not only that, once you are done with the evolution, in order to extract information about these wave functions, quantum mechanical wave functions, you need to have a lot of computational capabilities as well, because now the information of these wave functions is kind of an exponentially large possibilities for the amplitudes of these basis functions, right, in your final state. So again, there are strategies to deal with this kind of problems, but not necessarily for these strongly interacting quantum field theories. We don't have yet the full picture, and that's one of the areas of development to understand how to deal with this. But in principle, if you have a quantum computer that can store information, an exponential amount of information in the logarithm of the number of possibilities in terms of the qubits, then at least you start to manage the size of the problem in a quantum mechanical way. So that's kind of the idea, but I'm not going to go there until the second lecture. For the moment, we would like to understand how to express lattice gauge theories in the language of Hamiltonian formulation for today. So in the lecture notes that I will post, I have an example of a system of spins sitting in a 1D chain, so that you get a sense of what it means for the dimensionality of the Hilbert space to be increasing so fast. So even with a simple spin 1/2 system, you should be already see that not only the size of the Hilbert space, but also the size of different symmetry sectors within the Hilbert space could still be very large and not manageable with the current classical computers, even for small systems. That's why Hamiltonian formulation is so demanding compared to the Monte Carlo simulations of path integral, because there we can actually do important sampling. So let's actually, with that introduction, let's now talk about basis states in Hilbert space. So now we want to talk about the Kogan and Susskind formulation of lattice gauge theories. What I will present here again is a very short introduction to the topic, kind of summarizing what I have already discussed in the notes, so that you have the full picture in less number of pages to go through, but you also have more detailed descriptions and references in the extended notes that I will share, okay? So Kogan and Susskind formulation applies to lattice gauge theories. they could be abelian or non-abelian. So abelian as well as non-abelian. And it could be in any dimension in principle. Okay. So for the sake of this particular lecture, I will talk about the U1 gauge theory coupled to matter, and only one flavor of matter. And for most of the discussions, I'm going to also consider only 1 + 1 dimensions, although I talk about what would happen in 2 + 1D. 1 means the special dimension, and this other one is the temporal dimension. Because we're in Minkowski space-time, now there's a difference between a space and time. If we're in Euclidean space-time, we talk about 4-dimensional Euclidean space-time often. But now we are differentiating between the space and time. And you can already see why, right? Because in the Hamiltonian formulation, if your Hamiltonian doesn't have an explicit time dependence, that the only time dependence is really coming in this time evolution operator, which turned out to be a continuous variable. For the sake of lattice gauge theories in the Hamiltonian framework, the time is not going to be discretized. It's just a parameter in the unitary time evolution in the system. Hamiltonian, on the other hand, would only depend on the special extent of your lattice volume. And so that's why we, for 1 + 1 dimension, for example, we only have one sort of a special component for the fields that we are going to talk about. We have to be careful about the time component of the gauge fields, which is the next thing that I'll tell you about. So the way that Koget and Susskind suggested that you can think about the Hamiltonian formulation, and in fact, they show that it is identical to the path integral formulation by Wilson, or the Lagrangian formulation in their seminal paper. The starting point is to go to a temporal gauge. And of course, we have the gauge freedom in lattice gauge theories. We can fix the gauge. And one of those gauges, which is not a complete gauge, so it doesn't fully fix the gauge, but it's a convenient gauge, is to set the temporal extent, the temporal components of the gauge length equal to 0. Okay, so if you're in 1 + 1 dimension, the only remaining component is going to be A1. So I would just remove this and then just call this just A, because there is no A sub 0. Okay, so we should be careful about the implication of this, and in fact, be careful about what information we might be missing in the language of Hamiltonians if we set A0 equal to 0. This is a topic of an exercise that is kind of important, and it is in the notes, and it would allow you to actually derive the constant of motions from the Hamiltonian formulation, which have kind of this one-to-one correspondence to the language of the Lagrange multipliers in the Lagrangian formulation. And the A0 is that Lagrange multiplier. So if you're setting that equal to 0, we will be losing the information about that constant of motion just in the Hamiltonian itself. So if someone would write the Hamiltonian in this gauge for you, you have to also augment that Hamiltonian with the constants or constraints on the Hilbert space. Okay, and this is really very peculiar with the lattice gauge theories, because in gauge theories, there are local gauge transformations that leave the physics invariant. And then once you go through transforming from Lagrangian to the Hamiltonian framework, then you end up having to impose these local constraint or symmetry constraints on the Hilbert space itself. And this is kind of important. So these constraints are called Gauss's law constraints. So we will come back to the explicit form of these constraints when we talk about U1 gauge theory and its Hilbert space. But for the moment, just keep this in mind. Okay, now that we are in the temporal gauge in which the A sub 0 is equal 0 and there is only one gauge length, what could be the degrees of freedom to build the Hamiltonian from? Well, one way is to start from the continuum QED Lagrangian, which is just simply for just one flavor of the quarks, it's just simply some field psi times d slash, this is psi bar, psi, for the case of free fermions, okay? And then, of course, we know this is being gauged, and you can add a mass term, and then eventually also the interactions of the gauge links. But you can start from this continuum theory, then stagger the fermions, and then therefore go from this two component in the case of 1 plus 1d, go from a two component fermionic field that is sitting at each side to a one component fermionic field that I'm going to just call psi, that is sitting at the position X on the staggered lattice. So in the original picture, you have these sites with two component fermions at each side. And then in the staggered picture, you end up having twice as many sites as before. And now on each side, there sits this one component field psi, okay? So I have an exercise as a bonus in the lecture notes that you can follow through to take you from the continuum QED Lagrangian in an unstaggered lattice to a lattice Hamiltonian with staggered fermions, which is exactly what Koget and Susskind did in their original paper. I have given the reference to the paper as well, and some hints about how to derive this, okay? And what you should find out is that for the Hamiltonian, at least the first part of the Hamiltonian, which I'm going to call it a hopping term, you will have the following interaction. So H hopping is I over 2A for J, and then psi dagger. So remember, these are now just one component fields. So there's no gamma matrix in the picture anymore. These are just the usual complex conjugate of these one component fields. At site J, now we're on the lattice side, so I'm going to call X to be just J. It's just an index. There is a field U. I tell you about what this is. Psi J plus 1 minus the Hermitian conjugate, because I put an I in here. And what this is representing are fermions, this one component fermions, and let me call this with J now. Along with a link that is sitting at the link between the two sides. And what this interaction does is to allow the fermions to hop in between the sides or nearest neighbor sides while changing the quantum number associated with the gauge link. I haven't told you about the gauge link and its quantum numbers yet, but we'll get there, okay? So again, J are the lattice size. I'm gonna index them from 0 to n minus 1. And in fact, for open boundary conditions, this is what it should be. And for periodic boundary condition, this can go all the way to n minus 1, so that the last link could actually also connect to the first link and identified, the sites to be identified. So this would be the periodic boundary conditions, OBC and PBC. And you can imagine other boundary conditions as well, of course. A is the lattice spacing of the staggered lattice. So this distance between the two fermionic points. And now with that, we have to also define the U, okay? So this is already one term in the full Hamiltonian. I haven't told you about the other terms, but the other terms would be essentially corresponding to the conjugate variable of the U field, which is the electric field. From the gauge theories, you know that the pure gauge theories can have contributions from electric fields as well as magnetic field to the energy or the Hamiltonian. And in this case, if we are in 1+1 dimension, we only have to deal with the electric field, as we will see, not the magnetic field. So that requires that we define also an electric field, okay? So what is U? The gauge link, as well as the conjugate variable. So the gauge link, which is Uj, which is U defined at link that originates from side J, is E to the I, A, G, A sub J, where G is the coupling constant. Okay. So in the usual way that we write down lattice gauge theories, even in the Lagrangian formulation, it is more convenient to define the gauge links through the gauge fields through these linked variables. All right. And again, remember, because the A sub 0 is set equal to 1, really sort of the U sub 0 is, this is 0 is going to be equal to 1 and trivial. So that's why I only have one link variable, and the J is the site index now, okay? So because of this is just the index for the temporal direction. Because of this dynamic is trivial for the U sub 0, and therefore we only have one kind of links in 1+1 dimension. But also if it's in higher dimensions, then we have to introduce a directionality index to the U as well. In 1+1 dimension, it's just one of those variables. And again, J is really sort of the index side now for 1+1D, okay? All right, so what about the electric field? Well, it turned out that the electric field, as I said, is the conjugate variable of the gauge field, okay? and dot is just the derivative with respect to time. And because of this relation, these are quantum mechanical operators, and therefore their commutation relations would read as following. So if this is at side J, this other guy is at side K, then this turned out to be I over A, delta of J and K. So these conjugate variables would commute if they are at different sides, but they would not commute if they're sitting at the same side. And the commutation is defined up to this factor A for dimensionality reasons. Okay, so I can rewrite this as A times G times AJ, and then 1 over G E sub K to be just like the canonical definition of these commutations for conjugate variables. And one of the reasons I did this is that if you look at the definition of U in terms of A, I times AGA, right? This factor is that in the exponent of this guy. We use right. So A times G times A sub J has the following property because it's sitting at the exponent, and the dynamic is not going to change by changing this by a 2 pi shift, right? So we can limit this to 0 and 2 pi, and anytime you cycle by 2 pi, you basically get back to the same point in the same physics, okay? So now given this commutation relation over here, and given this cyclic property for AGAJ, you can already see that E or 1 over G EK is the generator of cyclic translations in variable A, G, A sub J. And if you remember from quantum mechanics, this is nothing but a quantum rotor. Okay. It's a 1 plus 1 D case with this particular commutation relation. So it's not quite harmonic oscillator, but it's a quantum rotor. And as a result of this property, the Hilbert space or the excitations of the gauge fields or gauge lengths, gauge degrees of freedom, are discrete. Discrete, and in fact, integers. Okay. So keep this in mind when I come back to build the Hilbert space of this theory. For the moment, I just wanted to introduce the fermionic fields as well as the gauge degrees of freedom, which are these two conjugate operators, U and E, that I'm going to use to construct the Hamiltonian. The U already we have used to make gauge invariant couplings between the fermions. And now the electric field term is going to give us the other term in the Hamiltonian, which I'm going to call H electric, which is equal to E squared with sub J over all the sides over J. And just for dimensionality reason, because H is supposed to be having dimension mass, I have to multiply this by A. And if you remember from the usual classical electromagnetism, there is the electric Hamiltonian is E squared over 2. Again, you can recover the same continuum QED Hamiltonian from this form, obviously, in the limits that you take the lattice spacing goes to 0. So this is now an interaction that is sitting on the link between sites J, j plus 1, there's going to be an electric field that is sitting at site, at link that originates from site j, okay? So this is another term in the Hamiltonian. What else we have to worry about? Well, we are in 1 plus 1D, but how if we were in higher dimensions? How if dimensionality was bigger than 1 plus 1D? Okay. So again, in order to make the connection to the continuum QED more clear, I have an exercise that would allow you to start from the Lagrangian of QED, for example, in 2 plus 1 or 3 plus 1 dimension, and then derive the Hamiltonian. And as you will see, if you are in dimensionalities that are less than 2 plus 1, you will not have the magnetic field term, okay? Remember, in electromagnetism, the Hamiltonian is proportional to also E squared, but also B squared, right? What about that B squared type term in this lattice language? As I said, in 1 plus 1 dimension, we don't have it. And it simply is because you're not sitting on a plane. And if you're not sitting on a plane, there's no way to define a magnetic field or a magnetic flux, right? So in one special dimension, this is not possible. Analytically, you can see it through going this exercise that I've designed for you in the notes. So, but let's say that we are in higher than 1 dimension, so that we have also an HB term for this QED theory on the lattice. And it turned out that you can recover the same continuum B squared type interactions from the following Hamiltonian, which is A over G squared, sum over J. Now I have to also introduce the index for directionality because we are in more than 1 dimension. Trace over 2 minus U plaquette along mu nu direction, U plaquette, mu nu dagger, where this plaquette operator is defined mu nu is defined as following: uj along the mu direction, uj plus e mu along nu direction, uj plus e sub nu. These are unit vectors along mu and nu directions. Mu dagger, u nu dagger along j. And again, pictorially, we can write this as following. So we have site sitting here. So this would be site J. And then this would be direction mu. This would be direction mu. So then we would be interested in multiplying the links that are originating from site J along the mu direction times the u that originates from j plus e sub mu along the nu direction, and so on. Okay. For QED, this trace is a trivial operation. Because the theory is just like one-dimensional in a sense. But for non-abelian theories, it's a non-trivial operation, of course. We have to take the trace, okay? But just to be general. And in any dimension, this generalizes. So this could be either 1 and 2 for 2 plus 1, but it could be 3 or even 4 and so on for higher dimensions, right? And these are the Cartesian directions along the lattice. So you must have already done this exercise of deriving the plaquette action and then deriving the magnetic type interactions from the plaquette action in the lattice gauge theory course. So it's very similar to what you should do in terms of the small lattice spacing expansion of this expression to recover a field that looks like b squared over 2 for the Hamiltonian. So I'm not gonna dwell on that too much because it should be very familiar. And again, if we are dealing with the U1 in 1 plus 1D, we don't even have to worry about this term. It's kind of complicated term. And as we will see with the quantum simulation approaches, it is very non-trivial to simulate this plaquette term because it requires multi-body interactions. So it can make the computations, whether in digital or analog form, far more complicated. However, of course, we have to deal with it. This is part of QCD Hamiltonian in 3 plus 1 dimension. So the only remaining bit about the Hamiltonian is what is called a master. And I'm gonna call it H sub m. This is just some bare mass times sum over the sites, minus 1 to the j, psi dagger j, psi j. Again, remember that these psi fields are now just one component field. So again, I'm back to 1 plus 1D because if you're in the higher dimensions, so maybe I should make this part distinct from the rest because this only applies to 1 plus 1D, higher than 1 plus 1D. And now I'm back to 1 plus 1D, where I'm dealing with just one component fermion sitting at this staggered site. And you can see that by going through this exercise that I have put in the notes, you will get this minus 1 to the j, kind of what the staggering means. The fermions at different sites come with different masses. And this then accounts for the notion of particles and antiparticle contribution to the Hamiltonian, because kind of we lost the information about the two component field and its dagger that would have the combined information from particles and antiparticles. Now we have to kind of distinguish these two fields in that regard, and that's where that minus 1 to the j comes from. Again, I have an exercise that will give you the hints of how to derive this from the original QD Hamiltonian in the continuum, and then to the lattice, and then a staggered. All right. So with that, we have 4 terms that we have constructed, one of them only for higher dimensions than 1 plus 1D. So I can write the Hamiltonian of the U1 theory as H hopping, which is the gauge matter interactions, plus electric field term, plus matter term, plus also the magnetic term or the plaquette term, only if in 1 plus 1 higher than 1 plus 1 dimensions. Okay. So at least we have the Hamiltonian, and now we can start simulating things at this point because now we have the Hamiltonian. Before doing that, we have to also realize the Hilbert space, the basis states, and the Gauss's law constraint that I told you to be concerned about, because that's something that we have to keep track of as the constant of motion in the theory. I'll talk about that in a moment. I just want to emphasize now that it turned out that this form is kind of a general form for even non-abelian theories. So even if you gave me in SU2, for example, lattice gauge theory coupled to matter, overall, I would expect the terms that exactly look like the terms that I wrote down, but I have to generalize them now to the group elements and the representations of the fermions in the fundamental or whatever representation of that group that would make sense, so that I have the right formulation for also non-abelian theories, okay? So for example, for SU2, and I'm not going to talk about SU2 particularly in this video lecture because of the time, but I have put the same amount of details as with the U1 also for the SU2 theory in the notes, and I encourage you to look at them. There are exercises about SU2, but I have made them bonus exercises just in case that you don't have much time to go through all the exercises. You can prioritize the one that are regarding U1, which is simpler and manageable in the amount of time that you will have for these exercises. But then if you're really, really interested to go deeper and learn about non-abelian theories, then you should also look at these SU2 exercises, okay? So for SU2, just to convince you that it actually looks exactly like what we had, this is 1 over 2a, sum over j, psi dagger j, uj, psi j plus 1, plus Hermitian conjugate. This is going to be h hopping, just as before. Then we have g squared, so different convention for what's in front compared to the before, but that's just the choice. J, e sub j, b squared, summed over b. I'll tell you what this is. So this is electric field term. And then we have a over g squared, sum over j, exactly the form that I have here. So I can just copy and paste this over there. Okay, and then, so this is now the plaquette term or magnetic term, HB, plus also the mass term, just as before. What are the differences? Well, we have to be careful about now the meanings of these objects are a bit different because we're in non-abelian theory. And in particular, these psi's are now two components because we have SU2, and in fundamental representations, they have two components. So these two components have nothing to do with the Dirac components that we got rid of for 1 plus 1 or other dimensions. These are just the group elements, right? The corresponding components for the SU2 fundamental representation, okay? The U now is a 2 by 2 matrix because it's supposed to be an SU2 matrix. It's an element of the group. So it's not just a phase or a number anymore, just as with U1, it's going to be an SU2 matrix. If you're dealing with SU3, it's the same thing. It's going to be now a set of 3 by 3 matrices is going to be elements of SU3, right? And then your psi is going to be a 3 component in the fundamental representation of SU3, which is relevant for QCD. What about this electric field? For SU2, there are 3 types of electric fields because there are 3 generators of SU2, and these E fields are those kind of corresponding to those SU2 generators. So then we have to sum over this, and this is going to be the Casimir of the group. And now again, these plaquette terms are defined with these 2 by 2 matrices for SU2. So the trace is going to be non-trivial. And then now the mass term, the size are 2 component fields in the space of SU2. So there are kind of 2 terms that are sitting in this expression for the mass term. As I said, for SU3, then the generalization is straightforward, as you can see. The good thing is that for all these different groups, you can resort to the same structure for the Hamiltonian, open to generalizations that are necessary for defining the different fields. Okay. So with that, let's also discuss the Hilbert space. So next topic, basis states, Hilbert space, and constraints. All right, so let's first talk about the constraints. And let me go back all the way to this slide. So we talked about this, and now we're talking about the basis states, okay? So now remember that we have the Gauss's law constraints. And again, through one exercise, I have guided you through how to derive this constraint, at least for the U1 theory. I'm going to just write it down here, and then we talk about it. So this constraint is the following. The Gauss's law operator is defined as EJ minus EJ minus 1 plus psi dagger J psi J minus 1 minus minus 1 to the J over 2. And in this picture, so we have the site J. Okay, so this is the site J. And then we have an electric field from the previous, starting from the previous side, right? EJ minus 1, an electric field on a link that originates from the J itself. So this is coming in, coming out, and this is side J. What this Gauss's law constraint is that G sub J, so at each site J, this G operator would annihilate the physical state. Well, this you might remember actually from just electromagnetism. This is the usual Gauss's law that would tell you that the divergence of the electric field is equal to the charge density, right? And this is now the one-dimensional lattice staggered version of that Gauss's law, which is saying that the net amount of the electric field at a vertex that goes through a vertex has to be compensated by the electric charge. And in fact, this operator here, indeed is the electric charge, as you will see through one of the exercises again. Okay, so the flux of electric field has to be equal to charge. If it's not, then you have to reject that state because that doesn't belong to the physical Hilbert space. But in order to impose this constraint, I have to tell you how to build the Hilbert space first out of the basis states, so that then we can apply this operator to the states and decide which one is physical, which one isn't. How do we do that? Well, the Hilbert space, as I said, is built out of applying Hamiltonian on the vacuum state, where there is no excitation in the fields. Well, what are the fields? I already showed you the Hamiltonian, so you know that the fields are kind of the psi dagger. Operators are in the Hamiltonian, so these are just the single components, fermions for 1 + 1 case, which is called lattice Schwinger model. I should have said that before. Which is 1 + 1 dimensional U1 lattice gauge theory coupled to matter. This is Schwinger model, okay? Anyway, so the fields are psi and psi dagger, and then we also have the U and conjugate E at each side, and these are at each side, right? So these are the conjugate pairs. And remember, these were corresponding to a quantum rotor. Okay. So now with this information, we can, at each site, imagine that the state has two types of quantum numbers. One is fermionic and one is bosonic. So I can write the state to be just the direct product of the states at each site, and then some quantum number that is bosonic, sub j, direct producted with a fermionic quantum number sub j, where because NB sub j is bosonic, it can have values from minus infinity all the way to plus infinity in principle, right? And these are integers because, again, this is a quantum rotor. And the quantum rotor can be characterized by these integer quantum numbers. These are cyclic translations of this u variables, the a times g times a variable, as we discussed. Okay, so that's where this comes from. The n sub j fermionic is fermionic, so it could be either 0 or 1. And this is really the beauty of this staggered formulation, at least in 1 plus 1d. Now we have one single component fermion. So you either have a fermion at the site or you don't. And this would be corresponding to 0 or 1. So these are really sort of the occupation number quantum numbers for the excitation of the quantum rotors, but also for excitation of the fermions. Okay. So this is, again, important information. And now the action of the Hamiltonian is a function of psi, psi dagger, u, and e. So we have to figure out how each of these operators would act on a state that looks like psi. And at the end of it, we have to figure out how psi j acts on njf. Well, of course, this is either 0 or a state 0. It's 0 if n sub jf is already empty, but otherwise it gives you a state with less number of fermions, which is 0, and f is equal to 1. And then similarly for psi dagger, right? So you can build a relation because it's a usual fermionic relation. For the sake of time, I'm gonna not write it down, it's in the notes. But more importantly, what is the action of u on n sub b sub j? Because now this is the bosonic part. Of course, it doesn't act on the fermionic part, so that's why I'm just interested in this part. And it's going to be a raising operator. It's a quantum rotor. Again, we know the algebra of the quantum rotor. We can build up the Hilbert space like this. What about the electric field? This is sub j. Acting again on the bosonic part of the state is going to give me the number itself, this integer number itself, times the state itself. So basically, I have picked a basis state in which the electric field term is diagonal, but the u term isn't, right? So the hopping term is not going to be diagonal in these spaces, but the electric field term is going to be diagonal in these spaces. Of course, this is a choice. You could have picked another basis in which you would diagonalize the hopping term, and maybe if you're in higher dimension, the magnetic term, that is complicated, but then that would necessarily mean that you no longer are in a basis where electric field is diagonal in. No surprise, these are conjugate variables. We cannot simultaneously diagonalize them. So we're always faced with this kind of issue, which comes in when we think about computations and how efficiently we can express the Hamiltonian in given basis states to compute and simulate the theory, okay? And of course, the lowering operator is going to be the U dagger. So that's all the information that we really need to build a Hilbert space, right? And then act by a Hamiltonian on that Hilbert space, which is great. It's kind of simple for this U1 theory. On the other hand, I have also presented the information about SU2 lattice gauge theory, which is a little bit more involved, but it still follows the same logic. You have a Gauss's law or a set of Gauss's law operators that are defined locally. They are the constant, they are commuting with the Hamiltonian at each single point. So this is 0. So this is important information. And then you can also define bosonic and fermionic quantum numbers in the SU2 case, and then build the Hilbert space from. That I'm not going to go through. The lecture notes contain a very kind of detailed example of how to build the Hilbert space of a two-side theory. We have to be careful though, because the Hilbert space seems to be infinite dimensional. Why is that? Because these bosonic quantum numbers are infinite dimensional. How do we deal with them? I mean, we have to put a truncation, otherwise we cannot simulate either classically or quantum mechanically these theories in this formulation, and that's where we actually put a cutoff. So in B quantum number, we make sure that it's always between some cutoff that I'm going to call lambda. And of course, the limit of lambda goes to infinity is where you recover the right physics. But fortunately, it turned out for low energy observables or for time evolutions at short times, you only need a few of these integers, lambda in the Hilbert space, so that you recover the physics. And the convergence seems to be exponential, which is great. Okay, so one of the topics that people think about very seriously is the effect of this truncation in the Hamiltonian formulation on the observables of interest. Of course, depending on the problem, depending on the gauge group, depending on the type of observable you're interested in, you might need a different cutoff, and you might need higher cutoffs so that you don't have systematic uncertainty associated with this truncation. So one of the things to always keep in mind. But given that, then you can set your lambda to some fixed value and then build your Hilbert space. It's going to be still a large Hilbert space as you take the size of the system to become larger and larger. So then you can take the bulk limit and continuum limit, the usual exponential increase problem, and then the size of the Hilbert space that I talked about. In any case, there is an example in the notes that would guide you through how to build this Hilbert space, at least for a small system by hand, okay? There's also another exercise in the lecture notes that would ask you to do this using a computer code. So you can like pick your favorite program, mathematical or MATLAB, and just code how to build a Hilbert space and impose the constraints. Because you can already see that imposing the constraint would diminish or reduce the size of the Hilbert space, the vast size of the naive Hilbert space, to a very small sector. It's still an exponentially large sector, but also it's exponentially smaller in size than the naive Hilbert space. So by no means it makes sense to simulate a theory in this sort of naive and unphysical Hilbert space, because most of the states don't count, right, in the dynamics. And it's good to start the simulation in the physical sector. It's good to have constructed the Hamiltonian only in the physical sector, so it's a smaller size matrix, so you can perform your computations far more efficiently. And that's one of the computational challenges of this program, because if you are dealing with non-abelian gauge groups and higher dimensionalities, imposing this constraint already could be computationally challenging. As you will see with one of the bonus problems for the SU2 case in the notes, okay? So make sure to follow at least the exercises for the U1 case, because they would allow you to step by step go through constructing the Hamiltonian, the Hilbert space, and so on, as you will see in the notes. So at this point, I think I have said everything I want to say about topic number 1, except for the fact that you have to keep in mind that there are other formulations. And I kind of touched upon this subject because I told you that I could have picked probably bases in which the hopping term in the Hamiltonian would have been diagonal, but then the electric field would have not been diagonal. You can do the same game with a magnetic field term. And in fact, there are dual formulations which are based on this kind of a strategy, thinking about whether you're in group element basis or in irreducible representation basis, for example. And this becomes significant, particularly for non-abelian theories, because as I said, dealing with something like magnetic Hamiltonian, which is this trace of the plaquette, the product of four links, could be very complicated. So if you had a basis states that would make that computation of that term easier, that would have helped. But of course, then you might run into the problem of making the computation of the Hamiltonian in the electric field Hamiltonian more complicated. So there is a trade-off. And in fact, you have to find out in which coupling regime it makes sense to pick a basis state versus the other. For example, we saw that magnetic field term was kind of proportional to 1 over g squared, while the electric field term was proportional to g squared itself, where g is the coupling. So in the limit where g goes to 0, which we call the weak coupling limit, obviously HB is dominant compared to H sub E, right? But in the limit of g goes to infinity, which we call a strong coupling limit, HE is more dominant, right? So depending on the coupling regime that you're interested in, you can pick one basis versus the other, and then you have to kind of interpolate in between so that you kind of recover also intermediate coupling regimes. Or if you have enough computational resources and you have good proposals for how to do each of these terms in a single basis, you can just do the entire calculation in a single basis. No problem. You do not have to change the formulation. This is a very active field of research, particularly for non-abelian theories. Still, people are thinking very actively about how to most efficiently represent the degrees of freedom in such a way that you have already physical variables present, and then you have a good basis states for representing different terms in the Hamiltonian, where not a single term is too complicated to deal with, whether in the quantum simulation or in a classical simulation. I have mentions of various different formulations along with references in the notes, and I strongly encourage you to go through them if you're interested. As I said, this is an active field of research. This might become the next research project for you to figure out some of these questions that are out there. I'm not going to say much more about this, and in fact, for the rest of this lecture, I'm going to talk about topic number 2. So let me go back to the outline again for you. So we kind of covered this, and we talked about other formulations. One of the things that I really want you to go through in the exercises, and we're going to talk about it in the problem solving session, is to fermionize 1 plus 1D theories. This is something that you can always do with abelian and non-abelian theories in 1 plus 1 dimension. So please make sure to look into this before the lecture so that we can have some exercises on this and get familiarized with this. It turned out that this is a very good test study for quantum simulation with the near-term applications. So it would be good to know where this comes from. So with regard to the second topic, which is now, let's say we don't have a quantum computer, we only have a classical computer, and we would like to perform a Hamiltonian simulation on it, simply because we're interested in real-time dynamics. And at the moment, we really don't have the quantum computers with the capacity and capability that would allow larger scale simulations of these objects, these theories. So we have to start also thinking more seriously about advanced algorithms for classical Hamiltonian simulations. So this would be this topic. So let me grab this and bring it over here. Okay. And I have mentioned a couple of these approaches. I will very briefly, in maybe like 5 minutes, talk about all of these. The point is not to, this is just like one single lectures and not everything can be covered here, but the point is that I mention or throw out a few names and methods so that if you're interested and curious, you would go and look at the right places. And in fact, I have given some good, valuable references for this. With the exact diagonalization, we're going to try and exercise on that so that at least for the small checks and things, when you do the Hamiltonian simulation, it is useful to know how to start from the Hamiltonian all the way to obtain the observables, including dynamical observables for a small theory, just on your laptop. This is one of those skills that you should have if you start in this program. And it's not that non-trivial. In fact, it's kind of a straightforward, but it requires to at least work out one example from beginning to end to understand how to code this up before resorting to other pre-written algorithms and programs that are out there that would allow you to do this in more automated way. Okay. All right. So what are the different methods? Well, there is kind of an old method which is called a strong coupling expansion. This is very similar to what you have seen already in lattice gauge theory courses. It's kind of based on the fact that once you're in this either weak or strong coupling regime, you can start doing perturbative calculations. And in fact, in this Hamiltonian, in this basis that electric field is diagonal in that I introduced for the U1 gauge theory, you can start to build the Hilbert space out of the action of H on the vacuum, where this vacuum is the strongly interacting vacuum. So then you perform the usual perturbation theory techniques that you've learned from quantum mechanics to this problem as well. So you introduce the perturbation that would start to excite your vacuum. So in this case, you have an H, which is H hopping term, H electric mass term. And then in this strong coupling vacuum, which is an eigenstate of HE itself, then you start to add the perturbation, which is this hopping term. And this is what is in the strong coupling limit. It's a small perturbation. And therefore, you add and insert this perturbation multiple times. So if you want to do a precise calculations, you do a strong coupling expansion to higher orders, which means more orders in the perturbation around this electric field H with the hopping term. Okay, so there's a good reference by Banks, Kogan, and Susskind on the U1 case. If you want to see all the glory detail of how this is done, check out that paper. It's a very good read and it's an easy read. And I think would give a lot of intuition as well what's going on. And in fact, to some extent, it recovers the properties of low energy properties of the system and the spectrum and so on, which is interesting. But of course, we need non-perturbative methods. If we would have been lucky, we had like large computers, we could have done just like exact diagonalization. And exact diagonalization means that you now have the Hamiltonian in some basis. It has the dimensionality of the physical Hilbert space, unless you have not imposed the constraint, in which case you have to deal with a much larger Hamiltonian. But it's, in the end of the day, is a matrix represented in some basis states, right? By action of these different terms in the Hamiltonian. And all you have to do is to diagonalize this thing, because once you diagonalize it, you have the eigenvalues and eigenvectors corresponding to the spectrum, as well as the wave functions for your eigenstates. But also you can do other cool things with it. You can look at time evolution, because in the end of the day, algorithms that do time evolutions are based on exact diagonalization if the system size is, of course, small. If it's large, then you have to resort to more approximate methods and other more efficient algorithms. So you can do dynamics and things like that. So there is an exercise in the notes that would encourage you and guide you to do this Hamiltonian diagonalization and doing a real-time dynamics for a small Schwinger model system. Again, one of those things that if you're starting in this program, you really want to do it on your own to make sure that you understand all the interesting features before trying to automate this or think about even quantum simulation. It's good to get a sense of how this is done classically before even thinking about the quantum simulation of these systems. So I have some mention of these more approximate but more efficient diagonalization methods. But in the end of the day, the most important one of which is this DMRG, is very closely related to the approaches that people take also in the tensor network. So let me just directly go to tensor network approaches. And tensor network methods are based on starting with some ansatz wave function that is much simpler and less complicated than the actual exact wave function that you should do your Hamiltonian simulation with. How do you find this kind of more simpler and efficient representation of the states? That's an entire course of how to start building this kind of tensor network ansatz for one-dimensional as well as higher dimensional theories for spin systems, but also for some lattice gauge theories. So I encourage you to look at a reference that I have put in the notes, which is a PhD thesis by Stephen Kuhn on tensor network methods for lattice gauge theories. So in that context, there's some nice introduction to the method, but also how to perform lattice gauge theory simulations using tensor networks for both static and dynamical properties. And then you see what the limitations of these methods are, and why is that eventually we seem to need quantum simulation for these kind of Hamiltonian simulation problems, still with a lot of progress being made on the classical side. For Hamiltonian simulation program, we are very much limited in what we can do or the community can do. So that's why everyone is excited about the prospect of quantum simulating and lattice gauge theories, but it's still the underlying theoretical framework is this Hamiltonian simulation. One way or another, I told you about one formulation, which is Colgan and Susskind. There are other ways to approach this, just like with the lattice gauge theory program, and you can have multiple lattice actions that recover the same continuum physics, you can have multiple formulations on a discretized space-time lattice, or not even discretized in a sort of continuum way. But in the end of the day, they have to be in the kind of the same universality class and recover the same continuum physics that you're interested in, but the starting point could be different. I told you about one starting point, it's kind of a standard, but now if I was able to make you motivated enough, you probably go and look and see what else has been done. And hopefully that lecture is really sort of the starting point for more investigations on your own. We will try to do a little bit more explicit examples and exercises during the tutorial and problem solving sessions in next week. But before that, make sure to check out the notes as well as the exercises and some of the quick sort of quiz questions that I have put for you for pre-class, pre-lecture preparations. With that, see you soon at the school.